Hey everyone, in this video we're going to go through the solutions to the homework test number 2. So I've marked the test so I can give you a bit of feedback about common errors and stuff like that as well, so just things to look out for. Question 1 was done really well, although those who got it wrong or didn't know how to approach it didn't recognise that both 81 and 9 can be rewritten with a base of 3. So the 3 here is a kind of giveaway because if you're simplifying an equation, it's always good to have the same base. So if you've got exponents, having the same base to solve the equation is good. So 81 is 3 to the power of 4 and 9 is 3 to the power of 2. And then you just go ahead and solve. Now an error that I saw, actually no, it wasn't this question, it was a further one. Actually, no, it was this one. So when you're dealing with your index laws, I did see some people do 4 times 2x. So they actually brought this 3 to the power of 2x over to the other side. And times 3 to the power of 4x equals 3 to the power of 4. And then when they brought got rid of the base of 3 and just dealt with the powers. But what you effectively have to do is add your powers together. Whoops, that should be a 4. So if you multiplied here, just remember your index laws. You're not to multiply, you're to add your powers. So when you're multiplying the same base, you add your powers, or as you can see here, when you're dividing, like we did here, I subtracted them. Now, you do get 4 over 6, but you do need to remember to simplify your fraction. So if you did not simplify to 2 over 3, you did not get full marks. So you've got to make sure you're always simplifying your fractions. All right, moving on to question 2. So this was done quite well. I was very pleased with this one because a lot of you recognize as soon as you use change of base, that's how you solve it. And some of you changed the base to 2 and some of you used E. You could actually use whatever base you like, but the answer is 16. I'm just trying to think of what common error people made. I'm not really sure, but it was done really well, which was good to see. Maybe some numbers incorrectly put places. So just make sure that your method's always correct. So you could get the answer of 16, but if there's incorrect working along the way, it doesn't mean you're always going to get full marks. So do make sure that if a question is worth more than 1 mark, that you do show working out and then that working out is correct. All right, moving on to question 3, another one that was done quite well. Just making sure, and we've done so many graphs now and I'm still seeing it, that people are not labeling their axes intercepts with coordinates. All right, so if you're not doing that, you're not going to get full marks. It was good to see your asymptote had the equation. All right, so it's y equals 4. But yeah, not labeling that, and I can see this doesn't go through clearly 3, but if I was not doing it on the computer, I'd probably be a little bit more accurate there. Now, some of you, you could have done this on your calculator to check, but it was probably a good sign that you weren't cheating and using your calculator to know what log base E of 4 is. So let's think about, I don't think you would get it in an exam, but let's think about, well, if you did, how would we know roughly what it's equal to? All right, so we're solving log base E of 4 is equal to 0. So not 0, to x. Whoops, oh, you're gonna go away, to x. All right, so if we're solving, we're solving for x. So we could rearrange this. This is the same as e to the power of x is equal to 4. Now, E is approximately 2.7. All right, so hopefully you know that. So it's Euler's number. It's just like pi. It represents a number which is approximately 2.7. Doesn't matter if you don't remember all the other digits that follow it, but remembering that it's at least 2 is important. Now, if I was to do e to the power of 1 is 2.7. E to the power of 2 is 2.7 squared. Now I know 2 squared is 4 and 3 squared is 9. So it's going to be somewhere between 4 and 9. All right, so if I'm doing e to the power of x is equal to 4, that means it's going to be somewhere between e to the power of 1 and e to the power of 2. So just drawing that intersection there. All right, because if I did e squared, it's going to be something between 4 and 9. All right, and e to the power of 1 is 2.7, and we want it to equal 4. Okay, so it's somewhere between 1 and 2. All right, your value of x, all right, is somewhere between 1 and 2. But I honestly don't think you would be expected to do that. But if you were, that's how you can work out what it is approximately. All right, moving on to question 4. So the inverse, I did see some errors with this one. So first of all, you need to have this notation with your solution. All right, you can't leave it as y unless you've defined y as the inverse. All right, so if you've defined it, that's fine. But if you just leave it as y equals and you don't go on to say f to the negative 1x is equal, then you're not going to get full marks. So I would hate for you to do heaps of work and then you just don't get that mark because you forgot to do the correct notation. You could even just go here and say, all right, so if you think you're short on time, you can just write it like that. All right, there is nothing wrong with doing that. Now, I did see some students have, don't know where along the way that they made the error, but I think they had the misunderstanding that 2 to the power of 1 over x is equal to 2 to the power of negative x, which is not the case. All right, they're not equal to each other. 2 to the power of 1 over x is 2 to the power of x to the power of negative 1. All right, so just getting your index laws around the wrong way. So just be careful and make sure you're confident with your index laws, because obviously you can't be referring to the index laws in exam 1. All right, you don't have your notes, it's not on the formula sheet, so they should just be second nature to you. All right, now as for the domain and range, so if we go back to the original function and consider the domain and range, and then remember for your inverse, they just switch. So basically, we want to say, well, what we have on the denominator, so x has to be, first of all, positive. So you can see it's there. So x has to be positive. It can't be 0. But it also can't be 1, because if x was 1, then the denominator is going to be 0. All right, so it's any real positive value excluding 1. Then for your range, so this whole fraction can't equal 0. All right, so we can't divide by 0, and nothing is on the denominator is going to give you that to equal 0. So you've got any real value excluding 0. So they just switch for the inverse. All right, moving on to question 5. Oh my gosh, it was so frustrating seeing this one. Now your period for a tan is pi over n. It is not 2 pi over n. Sine and cos, remember, are best buddies. All right, so they have everything in common. Poor tan is, you know, the third wheel. It is a little bit different. It's still in the gang, still in the trig gang, but it is slightly different. So the period is not 2 pi on n for tan, it's just pi on n. All right, so the period for this one is 2 pi. All right, so hopefully you remember that. And then the range, I saw so many students write the range was R, but your domain has been restricted. All right, so when you've had a domain that's restricted, it's going to influence your range. So basically you can just substitute in those 2 points, and we know for a tan function, it just goes like that. So it's not too complicated. So we're just going to substitute in 0. So tan of 0 is 0, and substituting in pi on 2. So pi on 2 divided by 2 is pi on 4, and which equals 1. So your range is 0 to 1. So a few of you got that, but yeah, some of you just wrote R. So just be careful of little things like that. So that was a 2-mark question. So yeah, very rare to get 2 marks. All right, question 6. So I did see quite a few of these correct, which was great to see. I saw some with like 10 solutions or so. So if you're given a question like this on exam 1, it's very time consuming to give 10 solutions. So that should be like an alarm bell in your head thinking, oh my gosh, I've probably done something wrong. I shouldn't be getting this many solutions. Not only is it taking you a long time, all right, so remember you've only got a short amount of time to show your skills, so they're not going to make you spend all this time trying to find all these solutions. And also someone has to mark it. So imagine trying to check 10 different answers. All right, so just think when you've got an answer, all right, how much does it make sense? Now, I know this is an exam question and I've made them up, and sometimes, I don't realize until I've done the solution, oh, this is probably not going to be an exam question, but something like this could be. All right, you've only got 2 solutions. Here they are, right? Negative 3 pi on 2 and 3 pi on 2. Now, you could approach this by using the general solution, which is fine. I approached it by just restricting your domain. So remember, we're solving for x on 6. So I just changed this x to x on 6. So whatever I did to the x, I then did to my lower limit and my upper limit. Now I got negative 2 pi on 3, which is kind of here, and then 2 pi on 3, which is here. All right, so I'm just basically working in this part here. I'm not going around my unit circle so many times. And that's what I think people did when they got all those solutions. And then you should probably check your solutions at the end, because they've got to be between negative 4 pi and 4 pi. So if you got 10 solutions and they're not between those two values, you need to be checking. So what I did when I looked at, well, what is my temporary domain? I know that my reference angle, pi on 4, is less than 2 pi on 3. So it's fine to be in between those two. And so basically we're just going 0 minus and 0 plus your reference angle. So there's your reference angle there. And then so we're dividing by 6. So the opposite of dividing by 6 is to multiply by 6. Okay, so we're left with 6 pi on 4, and then that simplifies. So just make sure if you didn't simplify that you now simplify. All right, you can easy fraction to simplify. All right, question 7. So looking at the general solution, this was done really well. I think some people forgot to solve for 3x and just left it as x. I think some students wrote down the general solution formula straight from their bound book and didn't really understand what they were doing. So just make sure you understand how to get the general solution without writing the formula, if that makes sense, because you don't really need to remember that formula. As long as you know where sine, cos and tan are positive in the unit circle, you'll be able to do the general solution. So if you're still stuck with the general solution, it's probably a good idea to get a little help either from me or from Mr. Reedy during the hour of powder. All right, moving on to question 8. So when I did this one, I actually drew it incorrectly. I translated it to the left. Oh my God, I've written it there still. It's gone to the right. Silly me. I'll just change it now. Actually, I've got to change it on my other solutions. All right, so it's gone to the right, pi on 2. So you can see my dotted pink lines. All right, so gone from negative 3 to 3. So this was done, probably the best question in the test. It was done really well. And then you can see my pink graph underneath is the graph of negative, without the translation. So just negative 3 sine x, and then I just shifted it. So when I initially shifted it, I shifted it the wrong way. So we wanted to go to the right, pi on 2, and that was done really well. So what wasn't done well though is writing your coordinates. All right, so not just leaving the point there. I mean, I can clearly see it goes through pi on 2, but you need to have these coordinates. Okay, so don't leave the coordinates off. And you can see there that the green is clearly my answer. But if, let's say the pink dotted line, I left it there to explain how I did the question. But if I did this on an exam, I'd probably rub it out or make it quite clear that this was the function. All right, so that's f of x. So you want to make it quite clear if you draw another graph before you did your translation. All right, question 9. So chain rule question. This was done really well. Interesting that quite a high number. So you might think, oh, I don't know my 27 times tables. Then you just need to do old school long multiplication. All right, it's a bit annoying, but yeah. Or you can say, well, basically this is the same as 8 times 9 times, well, negative 3. So 8 times 9 is 72. 72 times negative 3 is a little bit easier to do. All right, so just thinking about making it doable for yourself. But that was done quite well. Question 10 was done really well as well. So often these questions do end up just being 1, negative 1 or 0. Just because when you're substituting in whatever the angle is, it's yeah, quite a simple one. It's a reference angle, so you should know your exact values. Question 11 was done quite well, and I also saw someone do it a different way, which I was very happy to see. So actually, before I do that, I'll just explain. So a lot of you were able to get to here and then got a little bit stuck. So if we're multiplying fractions, all right, we multiply the top, so 1 times 1 up the top, and then we multiply our bottom, so root 2 times 2 root 2. So 1 times 1 is 1, root 2 times root 2 is 2, and then we've got times 2, so that's where you get your 1/4 from. All right, so I think some people got here and they were like, oh, I don't know where to go. All right, it is actually not as complicated as you might think. All right, so what I like to see, so what a student did, which I think is a lot more simpler, is she just did it to a half, like I did, but then brought that half out. All right, and then just dealt with the log instead of using the chain rule within the chain rule. So that was very good to see, because you can see here I did the chain rule within the chain rule. All right, moving on to question 12. So here we're using the product rule. This was also done really well. So I don't think anyone was scared off with the fact that we're dealing with sec squared, but remember sec squared is just the same as 1 over cos squared. I did see, which was a bit frustrating to see, so I'm just going to highlight this because this is what an error I saw, maybe 2, definitely 2, maybe even 3 times. So I saw people do cos of 2 times pi on 4. This is what I think they did. Cos pi on 4 is root 2 on 2, and then they did times 2. I think that's what was going on. But, I mean, that's wrong. This is equal to cos of 2 pi on 4, which is pi on 2. All right, so just, yeah, try not to get confused with those little things, because everything else could be perfect, but something small like that can make the final answer completely incorrect. But question was done really well, so it was good to see. Question 13, so also done really well. Just dealing with negatives and no fractions here though, but just being careful with that and knowing your exact values. But I think there was maybe 1 or 2, there was definitely 1 who turned it into a product rule. Now, you can turn a quotient rule into a product rule unless your denominator is a trig function and probably something else, but off the top of my head, it just is complicated if it's a trig function. So if we had something like let me just do an easy one. So let's say we had sine x over x squared. All right, so you could use the quotient rule for that, or you can say, well, that's the same as x to the power of -2 sine x, and then you could use the product rule. Completely fine. But with this one here, because your trig function is in the denominator, we can't say that cos of 2x and put a negative 1 there. All right, so we've got to be careful about that. So that's not 1 over. So we wanted 1 over cos 2x. So 1 over cos is, remember, sec. All right, so if you wanted to bring it to the top, you could change it into sec. And then you would find the derivative of sec 2x, which is beyond the methods course. All right, so just remember, if you've got a trig function in your denominator, you've just got to use the quotient rule. Okay, so just be careful of that. No, I should say that is not equal to that. 1 over cos 2x is equal to sec 2x. But you don't need to remember this because you should just be using the quotient rule. But yeah, done well, which was good to see. All right, question 14. So this was done really well. Marks were lost if students didn't do the coordinates. I mean, it's written there 3 times, guys, and I still don't see coordinates. So if you wrote x equals plus or minus √2, that is not a coordinate. All right, a coordinate has both an x there, so you can see negative √2, and a y coordinate. All right, so you have to have both. All right, so I've got my y-intercept at 0, 0. My x-intercept's also at 0, 0. Negative √2, 0, √2, 0. So there wasn't much space here, unfortunately. And my working out's a bit all over the place. And then to find the stationary points, so you'd find the derivative, which was done well, let it equal 0. But again, you need the coordinates. And I did run out of space, but I've highlighted there that 0, 0 is a minimum, 1, 2 is a max, and negative 1, 2 is also a max. Now you can see this funny drawing here. That's not me doodling. That is me actually graphing this function here. All right, so I know that is a quartic, and this negative in the front means it's a negative quartic. So a quartic usually looks like this, or not always look like that, but this one does because it has 3 stationary points, but it's been reflected, so it looks like that. So my 3 points, so the first one here is going to be your 0, 0, and there's your other 2 points, right? Because they're in between, what was it, 1, 2, and negative 1, 2. So there's 1, 2, and negative 1, 2. So it was good to see people use the gradient table to actually work it out, but you need to save time by thinking about what the graph would look like. And you can see that just saves so much time. You don't need to do a gradient table. You would use a gradient table if you didn't know what the graph looked like. All right, so let's say you didn't know what that looked like, you would do a gradient table, but that's so time consuming. Especially with a quartic, you should know what it looks like. All right, and there it is. Okay, this was graphed quite well, but again, I didn't have students putting, oops, sorry, I didn't mean to put that out, putting the coordinates in. All right, so you needed to do both the stationary points and the intercepts. So I did see some people do the intercepts, but not the stationary points. So to get full marks, you need to do it all. All right, so make sure you remember that. All right, I think that's the end.